environmental. And for us to have a grasp of what it takes, we have some learning objectives, and of which we believe that at the end of this interaction, we all should be able to identify major classes of inorganic and organic pollutants of concern in water. This one is not Nigeria being a country of concern now. This one is water pollutants now. And explain the fundamental steps that are involved in water sampling and preservation for different pollutant types. We should be able also to describe key analytical techniques used for the detection and quantification of inorganic and organic pollutants. And then the objective is that, as it continues, that we should be able to understand the importance of quality assurance, quality control in environmental water analysis. Then recognize the challenges and future trends in water pollutant analysis. Having said this, I think we should be ready now to move on to what water really means to us. I know we have all been told that about 70% of our body mass is water. And fundamentally, water is needed for life and the ecosystem survival. Consequently, if there is a pollution within this environment, this critical factor of existence, then it's a threat to human health. Human health in the sense that we drink water, we use water for every other thing we do. Even our recreational facilities are all tied to water. Then we have aquatic life, where some of the things that we eat too, the fish and the rest of them, are also threatened, and their existence too threatened. You have toxicity of the water body. You have the putrefaction of substances that are toxic to these systems. And once there is a shift in the natural balance of this ecosystem, definitely there is a problem, a major problem. A small shift, I will explain now. A small shift can cause catastrophic incidents. For example, the global warming thing we are talking about, just a 2 centigrade degrees to 4 centigrade degrees shift in temperature melts the ice at the Arctic regions, which floods the water bodies, oceans and all that, and cause devastating floods in regions that are beyond the point where this melting took place. Most of the flooding you experience in the last couple of years is just because of a 2 to 4 degrees melting of ice, increase in temperature and melting of ice. That's just the thing. So you can see how significant such things can be. The same with, like we discussed yesterday, the lava and the earthquake, landslides, even the tsunami is just a little bit of nautical miles away from land, and you see it coming into land. So it becomes a very significant thing when we start having pollutants threatening our existence. Now, we've talked about pollutants. What are these sources of these pollutants? We have the ones we call the point sources and the non-point sources. The point sources include industrial discharges, like I pointed us to the cassava alcohol producing factory here in Makurdi and so many other places where they have direct discharges to the water body around us. We also have direct discharges from sewage treatment plants. And these plants are all part of our activities. All of us pass these things and they are collected, and some industries don't handle them well and they discharge indiscriminately into the water bodies around there, which makes it difficult for everybody to access this water body, particularly from that point source directly into our homes. You need to go through some treatments to be able to have those things done. Now, we also have landfills. A typical example is the open landfill that we experience around the new bridge in Makurdi here. Though with the construction of the flyover and all that, they are excavating and removing them. God knows where they are dumping them. Those are some of the things that we have. And these open landfills, as far as we have them in the open and we have rains coming in or even water filling up from the River Benue bank, you have leachettes. Leachettes are materials that are extracted from a particular substrate via solvent dissolution, desorption, and all that. And it is released into the environment where it is not originally harbored. So we have all those kind of things coming in. And for those of us who are close to Makurdi and knows Makurdi, on the other side, you have vegetable gardens with these leeches getting into these vegetable gardens, and we harvest them and we eat. They come to the market. You don't know where they are coming from. You go there and buy your vegetables, not knowing they are from these leeches. Leechet fed farms. And we buy and we put in, we ingest. So these are some of the examples of point sources. The non-point sources are the agricultural runoff, pesticide and fertilizer residues. You apply a pesticide or fertilizer. For example, you apply a handful of fertilizer to your farm. The plants only get a part of it. The rest seeps into the soil. And when there is a rain, the rain comes, floods the place, and pushes it out. It goes and travels distances into water bodies, into other lands that we are not even having the pesticide or fertilizers applied on them. Now, when this happens, you have contamination of those places. And the contamination of these places forms a major problem for everybody. These are non-point sources. That is, they didn't happen at the point where the application took place. So you discover that non-point sources can occur distances away from the actual point of incidence. And those ones are very dangerous. And of course, permit me to tell you a story of how soap was discovered. Soap was discovered in the Mesopotamian days by virtue of the fact that on the mountain hill where they go for sacrifice, this sacrifice they do, down the hill, there is a water body. And when they sacrifice the animals there, they do burnt offering and all that. What do you call them? The fat that are melted and they are deposited along the path stay there. And when the rain falls, remember that they are on a rock. The rain falls on this rock, leaches out the alkali nature of the rock, where you have metals like magnesium, which forms magnesium hydroxide or calcium hydroxide. This calcium hydroxide, as they are being used as runoff, react with the fat that has been accumulating from the sacrifices of these animals. And by the time they get to the water body down there, they form soaps. That's how soap was discovered. That's the inception of soap. So you can see what runoffs can do, what non-point sources can do. So you have these things in so many places. The urban runoff, where you have oil, metals, road source, all those things seeping into places that are not the original points of incidence. And of course, we have the atmospheric depositions. As we had with the oil, the air point, we also have regulatory frameworks, which we have mentioned some key regulations and driving some monitoring aspects, like the one we have with the Clean Water Act, Safe Drinking Water Act in the US, EU Water Framework Directive WHO guidelines, and others. This is just a bit of what we have. And like somebody pointed out in the morning, we didn't talk about the World Bank issue. Once you talk about WHOs and EUs and all that, you are also touching World Bank. World Bank encompasses them. There are many of them, knowing that these things play different roles in different places. Now, we ask ourselves, what is the purpose of analysis? We do analysis to ensure compliance monitoring, that's regulatory limits. We do pollution source identification and tracking. We also do analysis to be able to assess the ecological and human health risks. And we evaluate the treatment process that is most effective. Of course, on the other hand, we also carry out variable research on pollutant fate and transport. Now, I want to give the class a 5 minutes to 10 minute assignment. I'll allow 1 or 2 persons to respond to it. What do you think? The question is this: what do you think should be the fate of water found around a lake that is surrounded or filled with salt, like a salt lake? If that is the only source of water for a community that is spread as far as 250 kilometers radius, I'll give you 5 minutes to think about it, and you give me the response within the 5 minutes. I'll be listening to you while you discuss. You give me that in 5 minutes time. People are not talking, no. None, people are not talking. I'm not seeing you people responding.
Question again, please, sir.
Okay, you can unmute.
So please, you can repeat the question.
I said the question is, what do you think should be done to a salt lake that is the only source of water for a community that is about 250 kilometers radius and is the only source of water for them? What do you think should be done to such an environment?
Sir, a separation.
Good afternoon, sir.
To separate the salt.
My hands has been up since.
Hello, sir.
Hello?
Yes, yes?
Hello, sir.
Let the lady speak. Let the lady speak, please. Ladies first, before they will say we are discriminating. No?
It comes to question his ladies first.
Let me answer. Sir, there is a need for desalinization of the water so that the salt will be removed. Thank you, sir.
You are speaking English. Tell me what desalination is. You know, we didn't go to school.
Desalinization is removing the salt content from the water. Separation of the salt from water.
By what means? Just give me your information, your details, your knowledge. Let us all be carried along.
Well, to me, I think if the lake is the only source of water for that settlement, which is about 250 kilometer radius, if the lake is the only source of water and it contains salt in it, then a process of water treatment is most necessary. A water plant can be built And then the water will be treated so the community can use it.
Yeah, try if the thing will catch. No problem.
Good afternoon. Well, me, I'd say we can actually desalinate the water using reverse osmosis. That's like the most common one they used in Nigeria. I mean, if it actually produces clean, drinkable waters and it works for small communities or cities.
Reverse osmosis.
She has mentioned the process, reverse osmosis, which is fine. Okay. Can I have all that information?
The reverse osmosis will help in removing the salt and hello, sir. Hi.
Yes. Yes.
Hello,
I'm
sir.
listening.
The reverse osmosis will help in removing the salts, pathogen, and heavy metals, because these are what will make the water undrinkable. And to be able to use this water, we need to remove these particles or these pollutants. So
Good
in order to
afternoon,
get
sir.
Okay. Any other idea?
Hello, sir.
Yes. Ms.
Yes,
Comfort.
yes.
Okay.
Yes, you can also use distillation method, which is boiling water to treat the water.
Yes.
When you boil the water,
Not only boiling water will go away now. Give me my hand now.
You can condense it now.
Boiling water, you cannot remove it. You can use so many methods. You can use crystallization to remove the salt particle, or you even use fractional distillation. Give me hand now. I raise a hand since nobody is
How
talking.
about thermal distillation? Using
Nobody is calling.
distillation method and evaporation,
If
sir.
you give you hand, you're already talking. So who do you expect to give you hand? I think the boiling is common. That community members to fetch water, fetch it and boil it. All other methods will be difficult for the entire sanitized.
Bring my hand. No one giving.
Is that the best you can do?
When you put
Hello,
your
sir.
hand there,
Is that the best you can do? Simon,
sir?
Can you hear me?
can you respond?
Yes,
Can you hear
sir.
me, sir?
Good afternoon, everyone.
Hello.
Sir, can you hear me now?
Go ahead. We're hearing you. Go ahead.
Okay, I was thinking of the simpler way. They are talking about distillation, but only distillation cannot do it, except something like fractional distillation, where you will boil and the water will evaporate and recondense. You have clean water, leaving the salt behind. That's my one idea. Or we can even use crystallization method to crystalline the salt and leaving the clean water for the community to use. Thank you, sir.
Okay, any more? I will entertain one more person before I respond. Shia Benjamin, can you respond?
Yes, ma. Yes, ma.
Simon,
Yes,
you are on.
I'm here.
We are hearing you, Simon. Simon, who's Bishi?
Off your mic, oh. Off your mic if you know the talk, oh, I beg.
In addition to what Mr. Samuel said, thermal distillation is another process and most to say maybe cheapest, because I think distillation and the evaporation will help in getting rid of hello, sir. My network.
With you.
Okay.
I'm listening with you.
I said thermal distillation. Okay, I said thermal distillation will work, and I think we can consider it as the cheapest, in the sense that evaporation and distillation will help, because we have to like evaporate the water. Hello, sir.
Yeah, you are right. You are right.
Sir.
Yeah. Okay. Now let me
My network
respond.
is bad.
Okay, Mohammed, your hand has been up. Mohammed.
Yes, I've been talking, sir. I've been talking. I said thermal distillation, sir.
Okay, then
In
you
addition
can
to
bring down
what
your hand now.
Farmer said.
Okay.
Okay, sir. Okay, sir.
You all have the concept at heart, but the fact is that I expected you to say you can establish a salt producing factory around the place that would desalinate the water, harvest the salt for production and sales for venture capital investment, at the same time produce clean water for the community. I said this is a community of about 250 kilometers radius. So that community needs an economically viable ecosystem to survive. So the best thing would have been for you to establish a salt producing factory that will pick up the water, harvest the salt, pump out clean water to the community, and then it's a win-win for everybody. Is that clear?
Yes, sir.
All of this are welcome.
Okay. All right. Thank you. Now let's continue.
Okay.
Looking at
Sir,
this now, you find that.
Allow me to unmute everybody so that you can unmute yourself.
Go ahead.
Okay, sir, you can unmute yourself now.
Thank you. Now, this brief interaction has shown us that even the things that we may consider non-pollutants like salt, because we eat salt, can in excess become a problem. Imagine where you have water, you are seeing the water like you have with oceans and water bodies that have salt. You can't. So the best thing is to think of an economically feasible way of containment, at the same time sustainable approach. So if the river or water body is producing salt, we collect the salt, harvest the salt, process the salt for consumption, and of course sales, and collect the clean water for use by humans and other aquatic animals. So I just want you to understand that what you are doing as an environmental monitoring officer is not just on the side of theoretical practices, writing policy frameworks and all that. No, your results, your output, your outcomes can equally generate industries. Your output can trigger the establishment of certain industries in localities that will benefit the immediate indigenes or occupants. So have that at the back of your mind. The department is not just training you for the certificate's sake. The department is training you for you to be what? And from some of these little things that we are doing, you find out that, look, looking deep into it, you can do a lot of things. Now, the pollutants of water that we can classify as inorganic and some of them as organic can be harvested and sent to particular industries where the quantities are much. We can harvest chrome or chromium and send them to industry where they are used to do chromium dioxide and chromium 2 oxide and chromium 3 oxide for applications in certain industries. Nickel, the same thing. Copper, the same thing. Zinc, the same thing. Even cadmium that can be used for batteries and powerhouses, where the quantities are much. And these are examples of inorganic pollutants under metals and metalloids. So lead, of course, we know, though a poison, can also be channeled into other constructive industries. And then when it comes to nutrients, where you have high concentration of nitrates, nitrite, ammonia, phosphate, yes, we can harvest them after we have monitored, one, the location we have identified, two, the extent of eutrophication or their presence, and the time or duration accounted for. We can suggest the establishment of a small cottage recycling industry. I just want us to have that at the back of our mind as we go along. It's not about identifying them, knowing they are there and all that. What can we do from there? What can we do with the information that we have? These are important. All of us cannot just end up being doing the things we are doing right now. Some of us can also branch out. Some of you have ideas. Some of you have the access to cash. Some of you have access to connections that can give legislative and policy approved. So you can come together and, trigger up something that is just product-oriented, not just about theoretical concepts. That is what I want you to have in your mind. Then for water also, we consider other things like cyanide, fluoride, sulfide, chloride, and sulfate. In a country like Ghana today, they have a problem with fluoride, containing fluoride. And fluoride can be used as an insecticide, as a pesticide, in other forms, but in controlled quantities. Other parameters that are also considered inorganic and pollutants too are the pH of the water, the alkalinity of the water, the hardness of the water, the dissolved oxygen of the water, and we have radionuclides. Now, when we look at it, hardness, what is it? If you have experienced, I think most of us have also experienced that there are some boreholes that are sunk, and the water from those boreholes are not very suitable for certain things, such as bathing, washing of clothes. Before you use them to wash clothes, you discover that you use a lot of soap, particularly the tablet soap, to wash. These are water bodies that contain a lot of +2 metals, the calcium, the magnesium. So monitoring becomes very essential, very important when it comes to water bodies. And we need to do a lot to do that. On the other hand, the organic pollutants, these are, like we had with the air, the volatile organic compounds. We mentioned the toluene, we mentioned the benzene, ethyl benzene, xylenes, and the chlorinated solvents. We have the semi-volatile, not like we had with the air. The same things happen. And then we have the emerging contaminants, the ECs. And looking at the pesticide, you can see a lot of what we use today are pollutants, and we pour them, the glyphosates and the organophosphates. So we are also contributing to the pollution of the water bodies that we have. We have the pharmaceuticals and the personal care products. We have some of them are endocrine disruptors. And I don't think anybody will want to go through the process of consumption of some of these endocrine disruptors because they end up leading to cancer issues. Now, how do we go about our sampling? I want to rush some of these things because for us to be able to cover though you have the material, but we need to touch a lot of them because we don't have much time. Now, we have, like we had in the morning, the objective, where are we, why are we doing what we are doing? Surveillance, compliance, source investigation. These are very, very important. We have the selective representative sampling locations and depths. I want to point out here that for water sampling, there are particular ways or methods of collection of these samples. Sample collection has to do with a particular method. For example, if you are sampling a water body and you are inside a boat, You are required to collect samples from a particular depth sitting inside that boat. First of all, the container you are going to use, if you are going to work on a plastic contaminant, that is, your attention is on a plastic contaminant, you don't use a plastic container to collect your sample. You use a glass container to collect your sample. Now, what do? The container, I want you to imagine this. You are holding a glass bottle or a glass container to collect samples from a water body. Now, that as you are putting in the container, upturn the container, the glass bottle, let the mouth of the glass bottle face down while you hold it at the middle. That's the container or the bottle at the middle. Face down, dipped into the water. Don't upturn it until the depth of water reaches at least above your elbow. At least your elbow. It is at that point that inside the water, you will upturn the glass bottle and allow water to get into the container. As soon as the water is filled, of course, you allow it for a while, you raise it up very fast. You are collecting water at that particular depth. That is the standard approach for normal sample collection when it comes to water. You don't just go and dip and collect it from the surface. No, you take to that height. Same happens with the temperature and the pH. You also dip your thermometer in, or you dip your pH meter, your handheld pH meter, the field type, and collect the pH and the temperature at that spot where you collected the water sample and record immediately. While doing that, you have a GIS mapping of the spot. You just take the GIS reading, your latitude, your longitude at that temperature, at that particular spot where you're collecting your sample. When you collect from different samples, you come back, you feed this information into a GIS app, and the app will give you a map of the area where you collected your sample. This affects, one, your output results, because the temperature and the quality of the water in the morning may not be the same for afternoon, and definitely will not be the same for night. So these are some of the things that you guide against. Now, the other one is your location. You have to have a representative sample location. You may have 3 spots usually on a particular row where you collect. You collect from spot 1, the one at the middle, and the one at the other end. And at the end, you analyze them separately, and then you collect and take an average. That is at the end of everything. That is your sample design under your representative location. You also determine the frequency and timing. Like I mentioned, what you have in the morning definitely will not be the same thing as what you have in the afternoon, and will not be the same thing as what you have in the evening or in the night or at night, because certain natural conditions take place. The flow, the tides, the seasonal variations also impact the quality and quantity. Of course, you would have to deploy appropriate statistical methods. Now, what do you use in your sample collection? Remember, what we've just discussed is your sampling design, though I delve into your sample collection a little bit. Your equipment or your container has to be clean, inert materials. Like I said, if you're working on plastics, you don't use glass to collect. You don't use plastic to collect your samples. If you're working on other materials that are not plastic, you can use things like Teflon, which is an inert plastic material. You can use glass, you can use stainless steel, and please avoid contamination. Now, the techniques now, we have the grab sampling, which is simple and instantaneous. We have the composite sample type, which is when you collect from different points along the same row, you mix them up. That is, you form a composite of them and take an average of all that you have collected. You look at the time flow proportional to what you are doing. Now, for example, you can collect from a single row with 3 spots, and you collect in the morning, in the afternoon, and at night, and mix up the whole thing and take it as a representative sample of what happens at that particular area per day. Because you collected in the morning, you collected in the afternoon, you collected at night. These are time zones and time frames with different natural influences. So you can do all those stuff, and then you can also do what is called a depth integrated sampling, where you vary the depth of your sampling and your collection points, Of course, you can use auto samplers to pick up, like if you have a TDS meter with you, that is a portable TDS meter with you, you can insert the TDS meter at a particular point and take readings of total dissolved solids and the rest of them that comes with it. So that is what you do. Now, for field parameters, we can measure in situ where possible, though. Temperature, I've mentioned that. pH, I've mentioned that. Conductivity, I've mentioned that. DU, I've mentioned that. Turbidity, oxidation, reduction potential, ORP. And we need to record meticulously. Now, why do we need to preserve our sample? It is very, very important to preserve sample and handle them carefully, because it will help us minimize changes in the analyte concentration or speciation between collection and analysis. This is it's a natural thought. We don't need to overflog that. Now, how do we bring them to the lab? How do we preserve them? How do we handle them? Make sure the temperature is not more than 4 degrees centigrade, because at temperatures above 4 degrees, there is the tendency for biochemical reactions to take place. Microorganisms that are naturally supposed to be inactive become active, and their activity generates a lot of other pollutants and contaminants inside your material. Now, for certain analysis, like the AAS and all that, you discover that you need to acidify your samples as you collect them, so as to prevent metal absorption and precipitation, and of course to kill microbes that may interfere with your analysis. At the other end, you can basify, that is adding bases, and we have different acids that we add, we have different bases that we add, as shown on the slide. Now, for certain reasons, we can do what we call dechlorination by addition of chemicals like the sodium thiosulfate that is captured here, and for a particular reason, for a particular purpose. And for some reasons, we can also create a dark environment, protective environment. This is particularly for light-sensitive compounds. And even, let me take your mind to those of us that have seen water treatment plants where you have something they call filter. There is this filter they attach to the waterways, the pipes, that takes water from the source of water to the tanks. Those filters, after a while, you see them, some of them, if they are not covered, if they are not protected, they start turning greenish, brownish, and black. That is because they are exposed to UV rays from sunlight. So microorganisms like algae start growing, and when they start growing, they start changing the parameters of that water system, system. So while you are transferring your samples from the source where you collected them, you should also protect them depending on what you're looking out for. for example, if you are looking at pesticide residue, if you're looking at PARs and all the rest of them, you need to carry out this. So it depends on what you are really working on. Now, the other one is the headspace minimization for VOCs, volatile organic contaminants. Because when you create a space, the VOCs will leave the water body and volatilize and stay within that space created by you. And at any time you open the container to assess the sample that you've collected, they escape, giving you false reading and false data. But when you fill your bottle to the brim, no space for it to volatilize. So anytime you open it, or anytime before you even open it, the VOCs are still contained in that sample. These are some of the things we need to do to preserve and handle our samples correctly. Holding times, that is, how long will you keep a sample before it goes bad? So much. So you discover that you need to keep some of them for not more than, like we have on the slide, 14 days, some 40 days, all depending on what you are working on. For heavy metals, you can keep them as much as 6 months. For SVOCs, you can 7 to 40 days. It all depends. Then the chain of custody that we mentioned before, the legal documentation, tracking sample possession from collection to analysis to disposal. This ensures sample's integrity, as the case may be. So in all of this, you discover that, look, you need to be very careful with sample collection, because that is where the problem starts. If you are careless with handling, if you are careless with collection, first of all, or your design, your collection, your transportation and transfer from point source to where you are analyzing in the lab, you may end up having a result that will give you a result that is false or not consistent with what somebody else might present later. And now we have arrived in the lab, and we have seen what is going on in the lab. What equipment are we looking at? We have gone through this before. I will briefly mention them so that we progress very quickly. We have the atomic absorption spectroscopy, which is AAS. And then, of course, we know under AAS, the atomic absorption spectroscopy, we have the flame AAS, we have the graphite furnace, we have the cold vapor, we have the hydride generation AAS. This is an addition to what we had in the morning. And these are all modifications of the conventional AAS that we have, depending on sensitivity and depending on the quality and characteristics of the heavy metal or metal we are looking at. We also have the inductively coupled plasma optical emission spectrometry, the ICP OES, and we have the inductively coupled plasma mass spectrometry, ICP ENS. These are based on what we are looking at. For ICP OES, we can measure to levels like ppm, ppb, that's parts per million, parts per billion. And same with the inductively coupled ICP MS, we have from parts per trillion to parts per billion. Depending on the sensitivity we are looking at, we will be able to identify and use the most appropriate equipment that is available for us to use, and in which lab we also try to locate a lab that can do this. And then these are things that we need to consider while taking our samples. For example, if, for instance, we don't have, in UNAGRIC, actually, we don't have the ICP OES and the ICP MS. We need to send them out. So we need to collect our samples close to the time for us to send them out. If it will take 2 weeks for the sample to arrive its destination, then we'll collect samples a day to the day we are sending out. and prepare whatever it takes for us to send it out. Now, under the electrochemical techniques, we have the ion selective electrodes, ISEs. These take direct measurement of ions, e.g., the fluoride ion, the nitrite ion, ammonia, cyanide ion, and they come as portable, fast, but limited in sensitivity and selectivity gadgets. But the thing is that they establish the presence of these things, and you can use them even on the field before going into detailed analysis with other more sophisticated equipment. We also have, like we have here in UNAGRIC, we have the colorimetric methods where we have a meter for analysis, and this colorimetric analysis, the colorimeter can be coupled with the FIA, that is a flow injection method, and we also can do a continuous flow analysis depending on what we have. For example, if we collected our samples with an impinger, we can continue the supply of the samples into our colorimetric equipment. As it runs, we keep recording our results or data as it comes. We also have the UVV spectrophotometry, which we have here in UNAGRIC, even in the college here. And anybody that wants to use such equipment or the UV, you are welcome to use them. This is also widely used for nutrients, the nitrite, ammonia, phosphates, and cyanide and phenols. And they are all available. And then we have the ion chromatography, which takes serious cognizance of separation and quantifications of anions as they flow into the column. So these are all equipment we can use depending on our target analytical procedure and the group. Then we have the analysis for the organic pollutants, where we have sample preparations and we have to be very careful, particularly when it comes to trace organic substances. Some of these organic substances are heat labeled and require careful handling. But we have the process of liquid extraction. Traditionally, you use immiscible solvents. You have two solvents that don't naturally mix together, but your target pollutant may be soluble in one solvent, but more soluble in the other one. But remember that they are not miscible. The two solvents are not miscible. Let's say you have a solvent, let's say methanol. Let me use solvents that we know. Here they use dichloromethane. If we have dichloromethane and methanol and dichloromethane cannot mix, but we have an analyte, we have a material that dissolves, let's say the rate of dissolution in dichloromethane, maybe say about 50%. But the same analyte, the same pollutant we are working on, has a 90% dissolution rate in methanol. If we use dichloromethane to harvest the analyte from the environment, all we need to do is introduce a quantity of methanol into that dichloromethane containing the analyte. And you discover that the analyte, as soon as it comes in contact with the methanol, migrates from the dichloromethane into the methanol. And as soon as it does that, it leaves the dichloromethane empty and finds itself in the methanol. Then you harvest the methanol. Of course, the methanol is not miscible with the dichloromethane, so they separate. If you put them in a separatory funnel, you see that one stays on top while the other one stays down. You run it off and collect the different samples with now separated analyte. That is the basics for liquid extraction. One, the first solvent must be able to extract the analyte from the environment where it is contaminating the environment. Then the second solvent that you are introducing should be able to have a higher affinity for the analyte you have extracted with the first solvent, so as to be able to extract it out, and it has an easier handling procedure as compared. For example, the dichloromethane is an organic solvent that is considered to have some health hazards implications, whereas methanol doesn't have such level of health hazards as dichloromethane. So you play safe by collecting with this one that has health hazard containing it, and then extracting the analyte of interest with the one that has less toxicity implication or level than the first one. Now, the other process of sample preparation is that you analyze using the methanol solvent sample or fraction. Now, the solid phase extraction, it's all about having a solid surface where your analyte moves through that surface based on their relative retention ability. For example, we use most times we use the C18 packed silica gel. When this silica gel is packed inside a column or a cartridge, as the case may be, it gives you the solid phase side. Now, the solvent, we introduce a solvent that has the analyte inside of it. Now, that sorbate is the solid, which is the cartridge. This is the silica gel, the C18, and it can conduct ion exchange by its nature and polarity, while the analyte, which is retained, comes with the solvent that you are pouring in. You have also used a solvent to extract the analyte from an original native source. Maybe that is where it pollutes. Then you pour it into the packed column with the C18 material as the solid phase or the sorbate. Now, when you are eluting, you discover that the small solvent that you have used in absorbing or extracting the analyte, as it passes through that sorbate, which is the C18, it separates mixtures of these analytes. They may be closely related mixtures of analytes, but because of the ion exchange potentials, they are carefully separated into individual analytes as they pass through that packed disc or cartridge, which is done with the C18 material, polymeric material. Now, different phases absorb different compound classes. So the solid phase separation process or extraction sort of separates closely related analytes that you find in a system. It could be a mixture, like you extract from, let's say, a water body, and in that water body, you have a mixture of PARs, you have a mixture of other organic material. They are all organic, which are not easily separated using systems or procedures like boiling and all that. When you pass them through the column, you discover that by ion exchange, they are separated into individual analytes. and you collect them as they run off the packed column. So in some of these things, you discover that you will carefully, using literature, identify the best, most suitable solvents for moving or separating these analytes from each other. Because while they were in that system where they were contaminants or toxicants, they had a synergy which enabled them to all stay together and not separated. But with such systems, you separate them and you collect them individually. Now, the other thing to do with this is to create a headspace, particularly for VOCs, where the sample is heated, volatiles, partitioned into headspace gas, which is injected into a GC. Now, remember, the GC operates best where the analyte is in the gaseous state. So when you introduce heat, the heat, as we know in chemistry, excites the molecules. These molecules, when excited, they tend to leave the environment where they are, probably the liquid environment, just like when you boil water. Water molecules at a particular level of excitement due to heating leaves the water environment, the liquid environment, and gets into the gaseous environment, which you see as the vapor. The same happens to VOX. On application of heat, the VOX leave the environment and move to a gaseous environment or space where they stay. And at this point, you introduce that space into a GC, and the GC, as they are passing through the GC analyzes what gas comes into each chamber based on set standards. This is a simple process, and it usually minimizes matrix interference. That is, each gas has a particular characteristics that it displays. So at that point, it is possible for the GC, when they're passing through that column and the kitchen, what I call kitchen, it is possible for it to individually identify them and specifically detect that so gas is what is passing and what is contained in this mixture. And of course, we then have the purge and trap. Also for VOX, where inert gas bubbles through samples, stripping VOX onto a sorbent trap, which is then heated, dissolved into GC, and this is highly sensitive, where you use the inert gas. For example, let me explain this by bringing in one method of essential oil production. There are different ways, but one of the ways is to use carbon dioxide that is under pressure. Carbon dioxide is an inert gas that does not react with things. And what do? You pressurize a carbon dioxide and release it to pass through the pores, spaces within the leaf. It ruptures the oil globules and carries them as it moves away from the leaves, only for it to be collected at a particular point when it is cooled and the CO2 is released into the environment, leaving you with only the clean essential oil. The same thing happens here with the purge and trap process, particularly for volatile organic substances. An inert gas bubbles through, and we have so many of the inert gases that we know, and you discover that they interact with the VOX, but not having any chemical interaction that disrupts their chemical integrity. They allow the VOX to remain themselves and retain their integrity, so that the GC would always easily identify them. But they are left without being drawn into the analysis. So they move with the VOX, deposit the VOX in a sorbent trap, and this trap then is what is introduced into the GC for GC to analyze the particular VOC that is present. This is a highly sensitive approach too. Now, we also have the quick, easy, cheap, effective, rugged, safe approach. This is popular for pesticide residues in a complex matrix. Remember I said that when we introduce pesticide in our farms or areas where we need them to do one or two things for us, and they happen to finish their work and moved out as runoffs, they enter water bodies, and we collect to analyze. How do we do it? There is this quick, easy, cheap, effective, rugged, and safe approach whereby the material is extracted with, that's the water sample collected is extracted with acetonitrile, and by dispersive solid phase extraction, cleaned up, separated individually for further identification. Now, the techniques that we employ, we have the gas chromatography, which we have talked about. We have the high performance liquid chromatography. Some people will say it is high pressure liquid chromatography. Well, it is high performance liquid chromatography. Both of them work under pressure, both the GC and the HPLC. Even the LCMS also work with pressure. We also have the ion chromatography, and we have the all these go through some detection techniques. Some of the detection techniques that we employ are the mass spectrometry, which is of a gold standard, the GCMS, which uses the electron impact ionization to be able to identify these analytes. Permit me to call them analytes. They are pollutants actually, but once we are carrying out analysis, they are analytes. Now, the electron impact ionization also ensures that, because it has the ability to analyze a lot of analytes that come its way, and from the already established or elucidated structures. It has a library of searchable spectra. So it uses that to match the analyte, the unknown analyte that employs electrospray ionization approach, or the atmospheric pressure chemical ionization approach. These are techniques that are deployed in the identification of some of these analytes that we throw in there. I would suggest we move quickly, and then what are the detectors that are coupled to one, the GC? We have the flame ionization detector. We have the electron capture detector. These are components that once these analytes pass through the GC and they get to them, they immediately detect that, oh, this is what it is. They all have their specific detection properties and limits and capacities. For example, the FID, that's universal for hydrocarbons and where they have good sensitivity. So if you use them for other materials, they may detect, but not with a very good and acceptable sensitivity. And the electron capture detector, ECD, they are sensitive for halogenated compounds like the PCBs, pesticide, and chlorinated solvents. Then we'll have the NPD, that's the nitrogen phosphorus detector. They are used for detection of the nitrogen phosphorus, nitrogen potassium ratio. For example, in pesticide, in mines, fertilizers also. because they contain the nitrogen and potassium and also phosphorus. Then you have the photoionization detector, PID, which is sensitive for aromatics and unsaturated compounds. So these materials are coupled to the GC. So you have a GC FID, you have a GC ACD, you have a GC MPD, you have a GC PID, depending on the analyte type that you're working on. Then you also have detectors that are coupled to the LC, that is the liquid chromatography system. We have the ultraviolet visible, that's UV-Vis detector. This detector is coupled to the LC. You also have the fluorescence detector. This is also coupled to the LC. The UV-Vis detector is used for common analysis of various materials that have the color luminescent outputs or chromophores, because chromophores are color releasing materials, organic groups. So for when you are detecting, when you are trying to work on a sample that has color or luminescence, it is most advisable to have a UV-Vis detector coupled to the LC. Now, the other one is the fluorescence detector, which is highly sensitive and selective for fluorescent compounds that can fluoresce at a material time. Such compounds are like the PARs and some pesticides. Now, if you have such material, the best thing to do is to couple the FLD to the LC. And we'll have the CAD, which is the charged aerosol detector. Of course, it's also the evaporative light scattering detector, ELSD. This is a universal detector for non-volatiles that have no chromophores. So if they are not having chromophores, that is color producing groups, you can use the ELSD or the CAD coupled to the LC for detection. Please be mindful of the fact that all these detectors and techniques have areas of best sensitivity, and we must be very careful so that when you have a sample you are analyzing, you don't just pick up any result and say, oh, this is the result of what we are looking at. No, the results have to be based on good technique of analysis. It has to be based on a good or correct coupling of these materials, the detectors to the machines or equipment. Now, looking at the quality assurance, I think we need to move. Let's go faster than this. These are self-explanatory, and I don't think we need to emphasize this, except replicates, blanks, key components, method validation before routine use, and all that. I want to skip this slide and look at this slide. I want to skip this too. Now, in conclusion to this, we have looked at accurate and precise analysis of inorganic and organic pollutants in water as being fundamental to understanding and managing environmental quality and human health risk. That is what we have established. And we have also looked at a rigorous approach that encompasses representative sampling with appropriate preservation and the state-of-the-art analytical techniques such as the ICP, MS, GCMS, LCMS, MS. And of course, we have also seen the very stringent QA, QC protocols, which are very important in maintaining reliability, validity, and integrity. Well, we also looked at the field that is continuously evolving, that is emerging fields, in order to meet the present and future challenges of detecting pollutants at even very traceable, very minute and trace concentrations, even within complex matrices, and to be able to identify the vast area of emerging contaminants. We've also come across the coupling of certain detectors in order to have an integrated form of advanced instrumentation and automation to be able to have good data science, which is key to the future. Without this, we can't predict the future. So what are the takeaways that we're looking at? The major takeaways here is the major takeaways that we can see is that we ought to know our pollutants. We need to know our pollutants, whether they are organic or inorganic. What type are they? What are they made up of? What is the, so to say, the chemistry around their properties and characteristics? And we are supposed to have handled the sampling and preservation that are critical and pollutant specific. It's not just about pollutants. What kind of pollutant are we dealing with? How are we supposed to handle them in order not to compromise the integrity and in order not to miss the mark of identifying them? So there are pollutant specific characteristics that we ought to also have, which we have seen. We have also been able to glance and browse through some of the equipment and some of the techniques and their complexities when it comes to the coupling with other aspects like the detectors and preparatory chambers like the FIDs and all that. We have the ICP, OEM, OES, MS, and all that, what they are for. We've also looked at the quality control and quality assurance requirements. This is very important for us to keep faith with the gold standard. And of course, we know that it's not optional. Is particularly the foundation for credible data that is required by us and other people. But we have the challenges that we keep getting trace levels and complex mixtures. And we believe that for the future, we need to do a bit more of process adjustment, technique modification, and enhanced data sourcing and analysis. And that is where AI and machine learning comes into play. And by the time we interface with them, we will discover that we just need to do the needful, and that is what? Accepting the use of AI and machine learning as part of a coupling component of the equipment that we have. That's a reference, and then we come to soil. Let's quickly run through soil and see what we have with soil. Just like air, just like water, soil is a critical component or compartment. Without the soil, we wouldn't have a base to stand. Of course, we know we won't have agricultural products to eat. We won't have places to build. This is the terrestrial ecosystem for plants, habitat, water, filter, carbon storage, and all that. the soil we know has a lot of uses that cannot be overemphasized. And the sources of pollution are the industrial discharges, which also happens with water, agricultural practices, discharges from agricultural practices, pesticide, fertilizers, just say agro inputs, as the case may be. Because in some cases, even the materials we use for mulching may at one time or the other turn to pollutants or toxicants, as the case may be. Now, we have also pollution from waste disposal, like landfills, either closed landfills or open landfills or all that. Then we also have pollution from mining processes. Just can testify to that. Enugu, the coal thing. And just like we have coal in Benue State, by the time serious mining goes into operation here, you start having such problems too. Then we have atmospheric depositions too from the acid rains and the likes. We have accidental spills, urban runoffs. These are very natural activities that helps in contributing to the pollution of the soil or ground ecosystem. What are these impacts? These things impact the ecosystem in a way that they cause degradation. Degradation principally is the reduction in the quality of a particular thing based on its initial standard or status. That is simply degradation. Now, the other impact is that it reduces the agricultural productivity and, of course, reduces groundwater quality via leaching. Most times you find out that wells that are dug close to pit toilets and soakaways usually, when tested, have certain microorganisms that are unhealthy, like the E. coli and the rest of them. These are some of the things because they permeate through the soil, contaminate the soil, and get into the water bodies on the ground. The other thing is what is known as bioaccumulation in food, because the plants pick up these things, and at the end of the day, they take them to the fruits, crops that we harvest and eat. So there is bioaccumulation in food chains and direct human exposure, where you have these feelings on the dermal, that is on our skins. We inhale a lot of dust that have these contaminants. For example, it is known that any person living in a metropolitan setting inhales a nanoparticle of a quantity that is capable of being used to produce an ATM card. It's also been established that humans within the metropolitan area have even nanoparticles embedded in their brains and seminal fluids. These are known facts. These are research confirmed facts. And generally, the impact of conditions of different kinds, damage soil, the structure, the biology, and of course, whatever biodiversity that is there. Then it now brings to bear the fact that there should be environmental monitoring. And if that is the case, what is the goal? It's simply for us to assess the extent, the distribution, and risk posed by pollutants to human health and environment, and to guide remediation efforts and regulatory compliance. These are normal things. And then our key pollutants concern, like we have other two, are also the inorganic and organic pollutants. And you take a look and see, you will discover that they are primarily the same, except for a few exceptions here and there, but they are primarily the same. So what affects the air, affects the soil, affects the water. So, but the major difference comes from source contamination and pathway. But if you go through this, you will find out that they are virtually the same. And I'm not dwelling so much on that. Let us look at what we have. How do we develop a sampling plan? Find objective like we had before. Define objectives and develop a sampling plan. What do you want to do? What's your objective for the monitoring? What do you intend to establish? Are you looking at establishing a baseline? Or are you looking at confirming compliance or non-compliance? Are you looking at assessing the risk that is involved in having such pollution? Or are you looking at providing remediation approaches or mitigation approaches and verifying their efficacies and authentications? So it depends on what you want to achieve. That would guide your sampling plan. But first of all, you need to, after this, you need to identify your target analytes. What are the target analytes? We cannot at the same time be looking at one thing. Our interests differ. So you need to know your target analytes based on site and objectives. For example, people who work in cement factories are exposed to a lot of dust, fly ash dust, and all manner of particulate matter. Somebody from that environment or living within that area may be interested in particulate matter. Somebody who lives around an abattoir may be interested in what happens with the leftover of the burnt carcass, leftover of the ash. What does it do to the soil? So it depends on the environment you are interested in. It depends on what you are working on. Now, with this and the objective, you move to design your sampling pattern or grid. Are you going to take the random or systematic or judgmental or the cluster, as the case may be? You determine your sampling depth. That's to what extent am I going to sample? To what extent is it relevant? And to what extent am I going to have the exposure pathways? These are questions you have to ask that will guide your design of sampling or workflow. Then you move ahead to specify a number of samples you need to carry out. Then replicates number. It's advisable to have not less than 3 replicates per sample. Then your field blanks, then equipment and blanks. Establish health and safety protocols. What are the PPs you are going to use? What are the PPs you're going to use? Will you need a glove? Will you need a nose mask? Will you need a headgear? Will you need a boot, a rain boot? Do you need an apron? These are the PPs, the private protective equipment that you need to also understand their uses and the importance before going into this. So, and now remember we are dealing with the soil. We have your sample collection. What do you do with it? What equipment do you use in collecting your samples? You have a stainless steel augers or coras. But please avoid contamination before use. Ensure they are clean. Ensure they are not dumped after the previous use. Then we also have the Teflon coated tools for organics and VOCs. You have the glass jars and all that. Now, what techniques are you going to deploy? In the deployment of the techniques, you try as much as possible to minimize disturbance. You try as much as possible to minimize composite sampling. And you try as much as possible to to separate or identify your composite sampling against district sampling. Your composite sampling involves, like I explained before, picking samples from within a locality, different spots, and mixing them together and picking out of that composite as a representative sample of what you want to do. Now, the discrete samples are just where you pick from a particular location or point, and that is what you use in comparing or analyzing your data and your results. So you should be able to know which one would fare better with what you want to achieve. Now, you should be very careful to decontaminate your equipment after every sample collection. And of course, if you are carrying out a composite sample collection, you should be able to homogenize very well before you pick your representative sample from there. Now, the other one is preservation, immediate cooling 4 degrees centigrade, and not above that and not below that. And specific preservation for certain analytes, e.g. acidification for metals, no acid for organics. These are things we have done before. We've run through that, and I think we should move forward. Now, this is sample preparation pretreatment. I think these are self-explanatory so that we can run through quickly. Avoid volatiles, grinding, sieving, use ceramic grinders for metals, cryogenic mills for organics to avoid loss. These are very straightforward protocols that we need to adopt. Now, for subsampling, representative splitting, that's the RAFO splitter or the cone and quartering. These are methods that when you are getting into the field, you need to understand the approach of dividing your location into space. And the rifle splitter method and cone and quartering splitter, where you have a lot of the materials, that is sampling points, at a particular corner and at a particular angle. The rifle splitter and the cone and quartering tells us on how to divide points of collection within a particular land space. Within a particular land space, you can, for example, have a 50 by 100 land space, and you decide to divide that 50 by 100 land space into 4 plots, and per quarter of that plot, dividing it again into 4 plots, picking randomly from each of those plots and sampling. These are some of the methods we use for quaternary. Now, for moisture content determination, oven drying a separate aliquot to report results on dry weight basis. You take out of a particular portion and decide to find out the moisture content. You don't heat above 105 degrees centigrade. You heat at 100 degrees, between 100 degrees and 105 degrees, until constant weight is achieved. You heat for 30 minutes, you dry, weigh. Take it back, heat for 30 minutes, dry, weight, until you have a consistent, constant weight over 3 periods, 3 cycles of heating and weighing. That is how to determine your moisture content for your soil sample. Now, let's look at the sample extraction and digestion. Here, because it is not as readily accessible like that of air and water, there is an extra step that one needs to take here, which is the extraction and digestion process. we transfer the target analyte from the complex soil matrix into a form suitable for instrumental analysis. And here, we digest the soil or extract from the soil using a solvent, an appropriate solvent. Like we mentioned before, certain digesting solvents or solutions like the aqua regia and the rest of them are employed. And it is the extra that we subject to the further instrumental analysis. Now, for inorganic pollutants like metals and all that, the digestion is done using strong acids. Like I mentioned, aqua regia, which is HCl-HNO3 combination of 1:3. We also have the HNO3HF, that is hydrogen fluoride. We have HNO3 hydrogen chloride and hydrogen fluoride combination. It depends on what you want to do. And this is introduced into the soil sample, and using hot plates are heated to a particular extent, or you use block digesters or microwave assisted digestion, and we after that rinse it off with deionized and distilled water and collect the extracts, which we then take into the instrumental analytical section. Now, we also have the partial leachable extraction, where we have the use of weak acids, and it all depends on what you want to do. But the goal here is to let you understand that the material, the analytes you are interested in, are not easily available, but have to be extracted from the soil sample that you have collected. For organic pollutants, solvent extraction is done. We can do that by shaking in the appropriate solvent, or we'll do suckset extraction. But we have to work on the time, work on the solvent medium, and the concentration of the solvent and all that. We can also do ultrasonic extraction. We can also do what we call cold maceration. So these are all methods of extraction that we need to do before we carry out the analysis using the instrumental approaches. Then others are the pressurized fluid extraction method. We have the supercritical fluid extraction, where CO2 is used as a green solvent. And like I mentioned before, the microwave assisted extraction for certain organics, of course, it depends on what you are working on. Then we go into the purification cleanup, particularly for organics, where we remove the co-extracted interferences, that is fats, wax, pigments. And such techniques are the solid phase extraction, which we have discussed before now, takes place, or the gel permeation chromatography, our acid-base partitioning, silica gel and mineral column chromatography. These are just processes of cleaning up and identifying, separating and identifying the individual analytes for proper identification. That's what really takes place here. Then for VOX requires specialized minimal disturbance techniques, because they are very, very fragile in handling, because they can easily leave and they can easily be lost. We use the purge and trap concentration to do that, which I have discussed earlier before now. We also have the methanol extraction for less volatile VOX, SVOs, followed by dilution in water and P&T or direct injection. That is a purge and trap or direct injection. And then we have the instrumental analysis, where we, just like we've discussed before, the AAS, the ICP, OES, and ICP AES, and we have the ICP-MS. Where we have also the gas chromatography for the organic pollutants, and we have the HPLC, and then we have the detectors that have been discussed before. But now we have an addition of what is called the diode array detector, DAD. That is another type of detector that is now included for the soil analysis. So These are other techniques that we have also mentioned. Using the addition here is the total petroleum hydrocarbons, using GCFID, using specific methodologies like EPA 8015 modified. We won't have time to do that explanation, but it's something that we can always find from literature. Then we have, this is our quality assurance and quality control. Method of blanks, laboratory control samples, matrix spikes, certified references, data, and then we have interpretation. By interpretation, you look at the results you have obtained from your analytical exercise and compare with existing standards to be able to confirm whether your values are above or below standards or thresholds. That way, you'll be able to comfortably, mention the health risk that is involved, whether they are there or not. Now, what are the challenges and considerations that we are looking at? One, soil heterogeneity is a problem because one, the soil is not homogeneous, particle size, composition. You find a particular soil that has a quantity of humus, a quantity of loam, a quantity of clay, all mixed up. And that brings to bear the fact that this particular soil sample has different soil sizes, particle sizes. And that creates a challenge in the sense that adhesive or adhesions to some of these analyte samples may be of a problematic nature. Even the extraction, because you have surface tension playing out, even extraction may be a problem. Now, if you are looking at Vox in an organically dominated soil sample, it may require a modified method of extraction. If you're now looking at the same Vox in a sample of soil that has both organic and clay components, it also requires you modifying an existing approach or method or technique. So these are some of the things that come up with soil analysis. So one has to be careful in the analysis protocol that you deploy when it comes to soil analysis. Now, the matrix complexity, yeah, like I mentioned, organic matter, clays, iron oxides, this affect extraction efficiency. Yeah, I've just mentioned that too. Now you have the low-level detection. It's one of those things that you discover that it becomes risky to go through the process of extraction, preparation, and then getting high sensitivity, because by the time you go through all that process, a lot of integrity has been lost when it comes to the analyte state. And that brings us to the next point, which is the analyte stability. By the time they go through these treatments, acid wash or solvent extraction or whatever thing that you're going to do, you find out that the analyte may not be stable enough to stay in its state of integrity to be able to be picked up by any machine that doesn't have a very sensitive identification technique. So it becomes a problem, and it leads to lack of adequate validity measurement. Now, the other thing is the cost and time. A comprehensive analysis can be very expensive. Yes, it is. And it is slow because of the processes, the protocols involved in sample preparation, sample analysis, validation, and all that, and the equipment that are used in doing all that. So it becomes costly. It's also time consuming. Then the green chemistry aspect of it, reducing the solvent used in organic extractions, is a challenge which the scientists today are working on. That is why we have the ionic liquids and all those green solvents that we mentioned, where CO2 comes into play. There is also this continuous search for liquids that are not very dangerous to the atmosphere and to man, which is not very, very easy to come by. But we still have to keep looking, keep trying out one liquid or the other, particularly the ionic liquids. But the ionic liquids have their challenges. So it becomes very difficult to get direct replacements of these liquids when it comes to green chemistry aspect of reducing the solvent impact on the atmosphere. Now, the other challenge is that most of these analytes in their normal ground or natural state are not bioavailable. That it becomes difficult to extract them in their natural integrity or state. Because they are not easily bioavailable, it becomes another branch of research to develop a protocol that would extract them, separate them, and make them bioavailable for a very valid identification and recognition. So, what are the summary key takeaways? Soil pollution analysis is vital for protecting human health and environment. Yes, that is correct. And the rigorous multi-step process from planning to interpretation is essential. Method selection, extraction, digestion, plus instrumentation is dictated by the analyte, whether organic or inorganic, as I've just said, and requires sensitivity and specificity. The QA/QC is non-negotiable. We must adhere to that. And interpretation requires context, comparison to guidelines, safety protocols, policy frameworks, standards, gold standards at that, are very, very essential and cannot be compromised. Well, the field is evolving with advances in technology and a focus on greener and more informative methods. We can't stop. We must continue. And we know we'll get there. We're supposed to do sediment samples for inorganic and organic pollutants. But it runs through the same. And our time is up for today. And on this note, I would want to entertain questions, and we'll see how we move on. Thank you very much. Imana, thank you.
All right, thank you very much for the lecture.
Thank you very much, sir.
Thank you. You're welcome.
Thank you very much, sir. Well done.
Thank
you. Well done. Well done, sir.
You're welcome.
Well done, sir.
Thank you.
Mr. Francis, you can be.
Thank you, sir. Well done.
Mr. Francis.
Yeah, I'm here. I'm here.
Go ahead with your question.
Sir, I was very happy when you said what we are studying.
Sorry, if you are not speaking off your mic, please.
Francis is still here. Hello,
Francis,
sir?
go ahead.
Hello.
Francis, go ahead. We are listening.
Okay, sir. I said I want to actually appreciate you for telling us that what we're doing is not just theoretical.
Oh, this person, if you are not speaking off your mic.
The interruptions they are just too much. Sir, are you here with me?
Yeah, I'm listening, but I can't get you.
Okay, so I'm saying that I really appreciate you for telling us that what we are studying here is not just theory.
Yes.
It is something we have to put in practice.
Yes.
And you gave us an instance about a lake which is covering a very sizable community. And in the end, you profiled a solution that in such an environment, a salt factory could be provided that will extract salt for the use for the community, while the clean water is now distributed to the community for use. Now, I have a situation somewhere around Radio Benue Civil Service Commission to Achusa, where the water is completely salty. Now, this is not a lake. How can we extract salt from this place and be able to make this community water usable for our own benefits?
Okay, first of all, are you done?
Yes, sir. I'm okay.
First of all, you have to tell me the kind of water body. Is it a well? Is it
no?
Okay, so it's not a lake.
No. Even the boreholes around here are still salty.
Okay.
Yeah.
That's the underground water is salty.
The underground water is salty, it's rusty. Any attempt, what you see within a short period of time, everything is rusty, very high rust.
Yes.
So one cannot even make use of it.
Yes, that kind of water within that locality requires a deep well treatment system.
Okay.
Yes, there is a holistic approach to it where you separate both the salts, the metals, and the sulfite, because there must be sulfite.
Okay.
So it's something that is doable, but I don't think it's something we discuss in class. We can discuss privately if you want to go into that as a project. Because for each of those contaminants, there is a particular unit that will be produced to handle water from that source. And for the whole community to be free from that, it requires a major approach
by the government.
Yes, but you can have what is called a prototype to showcase what is known as a proof of concept.
Oh, that is wonderful.
But it is doable.
Good.
So you can come, we discuss it, and then we'll map out a process of for doing that.
Very good, very good. Thank
Yes.
you so much. Thank you so much.
You're welcome.
I appreciate it.
You're welcome. So the next question. Any other question?
Good afternoon, sir.
Okay. Kula, how are you?
Thank you, Doctor.
All right.
Thank you for the elaborate lecture.
You're welcome.
Thank you, Doctor. The question you just answered, that was the question I wanted to ask, because that's the area I'm living. So for me, I'm just, yeah, that's the area I'm living.
Okay. I think I would suggest to the HOD, people should do it as your final year project. Yeah, it is doable. It is doable. Yes.
All right, Doctor. Okay. Thank you so much.
You're welcome. Any other concern? Uche, you have not said anything. Uche Matthew. Uche, what are you saying? I can't hear you. What's going on? Any other question? Any other concern?
Okay. In the absence of any other concern, any other question? Hello?
Hello. Hello. Hello.
Hi. Hello?
Okay, I have a
Yes, I
question.
can hear you. I'm with you.
Okay,
Dapper.
my question. Okay, sir. Okay, last year I participated in a field exercise. I'm a geologist by profession. So we
Okay.
went to several sites within Plateau State. So we pick samples along the river and stream channels, and that's water samples, and then sometimes soil samples. And then most especially my interest is on we pick water samples from springs.
I'm listening. I'm listening. Hello.
Hello?
Hello.
So as soon as I unmute now, everybody will be saying what he wants to say.
No, it's better to regulate it.
Mr. Evans, you muted yourself.
Hello.
Yes,
Okay,
go
can you hear
ahead.
me now? Sorry.
Mr.
Yes, I can
Evans,
hear
can
you.
you continue to ask
Okay,
your
sorry, a call
question?
just came in, that's why.
Okay,
Okay, sir. So after picking the
Please be
samples,
fast. I'm not able.
yes, sir. After picking the samples, it was sent to the lab to analyze the chemical properties of the water samples.
Yes.
And we use those results to try to determine certain minerals that are characterized with certain elements and chemicals.
Okay.
So, and then at the same time, we pick water samples in most of the mining ponds within Jos Plateau to determine the properties of such waters.
Yes.
So this particular lecture is very enlightening to me because me, I've been a junior staff. I was just like those people that pick the samples, but I'm not in the picture of actually all the processes that the samples will undergo for us to obtain the results. So I'm grateful for your lecture, sir.
You're welcome. You're welcome.
And then one other thing, I don't have the presentation. I don't know if it is possible for us to have it on the platform.
It's on your student-only platform. Ask your colleagues.
Okay, sir. So thank you very much for.
You're welcome.
Okay, sir. Yes, sir.
Any other concern? Any other concern?
No, sir. I think we are cleared, sir.
You are cleared. Vera?
Yes, sir. Yes,
how are
sir.
you? You don't
I'm
have
fine,
you don't
sir.
have question?
No, I don't, sir.
So if we say question now for you, you will answer 100%.
Very well, sir.
Are you serious? This is great.
Yes, sir.
Okay. That's good. So I class. I'm ending the class. I can't see any other person.
Mr. Wange is saying his hand is up.
Okay, let you speak up.
Can you unmute yourself and speak,
Moses.
Mr. Wange? Moses.
Yeah, Moses.
Please unmute yourself and speak.
Hello?
Just tap on the screen of your phone. You will see where the mute.
Hello, sir.
Yeah.
Good afternoon.
Good afternoon.
Please go ahead, sir.
Thank you very much for the wonderful lecture, sir. Sir, I would, owing to our environment today, that we have sources of nanoplastic everywhere contaminating the water bodies around us. Is there any local facility here in the state or elsewhere in Nigeria or even in Jostone that we can carry out this water analysis to detect nanoplastics? Thank you.
Yes. I personally am working on nanoplastics. I've been working on nanoplastics. Detection of nanoplastics along the river Benue tributary of starting from Taraba and opening up to Kogi State. So yes, it's possible.
Okay. Thank you.
Thank you. Any other concern? Patience, you are not saying anything. You see how your patience, you're not saying anything. Daniel, do you want to say something?
Yes. Yes.
Okay.
Good afternoon.
Good afternoon.
Good afternoon, sir.
Good afternoon.
Yes, I was having issue of network.
Oh,
Just
okay.
I didn't follow, but the little I followed, I think is interesting and educative.
Okay.
So I just want to appreciate for you for the lesson. I've been trying so hard to have the lectures, but I keep on having issue of network.
Okay.
But at least I have captured something that is interesting, especially that of pollutant.
Oh, okay, no problem.
Yes.
I pray that the recordings will be available so that you can do a catch-up.
Yes. That would be great. Thank you very much. We are enjoying your lectures.
You're welcome. You're welcome. Yeah, Patience. I want to hear from you, Patience. Any other concern?
Sir, can I please share something?
Go ahead. Is that Moses?
Yes, sir.
Okay, go ahead, Moses.
I came across a new concept which I myself am still trying to go through it and study the details. But it has to do with camels.
Camels?
It has to do, yes, these camels that roam in the desert.
Okay.
You know, most parts of the world now, the desertification is taking over. And scientists are looking for innovative ways of making the desert green again.
Yes.
So I came across this article that they said the concept from the camels, the way camels breathe. You know, camels, they have, according to them, they have a special membrane that engages reverse osmosis, because in the desert and sometimes most water they take is salty, but they have special features that convert that salty water to fresh water, and it is used in their body. So scientists are looking for ways of using that in the desert to make a greenhouse that can convert this salty water, remove the salt by evaporating the water using those special membrane mimicking that of the camel, and then having fresh water that will be used in the greenhouse. And then they discovered that even the surrounding around the greenhouse was becoming green. So they are saying that using that concept now, they can turn the desert back to green. I don't know how feasible is that, but this was a little thing I was able to gather from it.
Yes, it's very feasible. However, the challenge is still at the prototype level. The challenge is the mass production of the membrane. You know, you have to customize that membrane to serve the same way that of a camel serves.
Yes.
And that of the camel, it has an internal mechanism for its cleaning up.
Yes.
And then this one, once you produce it and it's used outside, there must be another unit that will do what is called a backwashing of that membrane for it to continue its function. But that is not that it cannot be done. It is already been prototyped.
Okay.
And for anybody that is interested in that, it's okay. It's something that can be done. And I know very well that here at ENS, if anybody is interested, come, we can partner and work on that. All you need to do is meet the HOD, tell him about the concept, and tell him that I am also ready to work with such a person. He's the only HOD that can give that permission. But can we do it here at ENS? Yes. Can we do it here? Do we have the expertise here at Jostum? Yes. What we don't have is your commitment to do it. So are you ready to be committed?
Yes, sir.
If you're ready to be committed, then talk to HOD.
Okay, sir.
Yes. But the expertise is here. I'm a polymer chemist, industrial polymer chemist by training. And the membrane you're talking about is a polymer membrane. So I want to buttress the fact that we have the expertise here at ENS and Jostum.
Okay, sir.
You're welcome.
Thank you very much.
You're welcome. Any other concern? Any other concern? If you know you didn't understand this lecture, tell me now. I'm ready to go back the 2 hours again, no? So that everybody will understand it. Kelechi Joshua, you've not said anything since you came on board.
Hello, sir. According to our timetable,
yes,
this afternoon class is supposed to be 1 hour. Is it changed?
No, the extra 1 hour we did today happened to be a cover for the last 1 hour we didn't do yesterday because of a misinformation.
That's right, sir.
So we just used the extra 1 hour today to cover for yesterday. So we are not owing you any lectures. That is what we did. Instead of you missing that lecture.
Okay, sir.
Do you understand it?
Thank you, sir. Thank you, sir.
Everything still remains the way it is. Vera, you said you are interested. Meet HOD. Let HOD give the permission, eh? Any other concern? Now, with your good understanding, I want to end today's lecture and wishing every one of us a very good evening. Looking forward to tomorrow for another set of interaction with you. Thank you and stay blessed.
Thank you very much, sir.
You're welcome.
You can use
Thank you very much, sir.
You're welcome.
Send Oga some love.
Thank you, sir.
You're
Go to
welcome.
the reaction and send Oga some love.
Thank you, sir.
Thank you, sir.
Thank you, doctor. We are grateful.
Thank you very much.